Welcome back to The Explainer. Today, we're diving straight into the high-stakes reality of marine switchgear safety. And honestly, there is zero fluff here. We're looking at the raw engineering that decides whether a fault stays a localized controlled event or spirals into a total disaster at sea. I mean, when you're dealing with a medium-voltage switchboard that's feeding every single amp to a ship's propulsion and thrusters, you are dealing with an immense amount of energy. So we really need to understand exactly how this hardware is built to survive it.
Picture this scenario for a second. You're a marine technician. You're standing in a dimly lit engine room corridor right in front of a medium voltage switchboard, humming along at 6.6 kilovolts. And suddenly, an arc fault ignites right behind that closed metal door. What actually happens? We're talking about a contained explosion of superheated, highly conductive gas. This visceral, terrifying reality really sets the stakes for the hardware we're unpacking today, because your life and the safety of the entire vessel literally depends on the design of that cabinet standing in front of you. So to understand how we actually survive that, let's quickly look back at the foundational architecture of the switchboard. Just as a recap, we know these boards feature a metal-clad construction broken down into 5 distinct internal compartments: the bus bar, the breaker, the cable terminal, the secondary equipment, and the operating unit. It's kind of like a high-rise apartment building. If one unit catches fire, thick concrete walls guarantee it cannot spread to the neighbor's unit. That is exactly what this metal-clad construction is doing with rigid steel partitions. It isolates these explosions to a single sealed unit, one fault, one compartment, never the whole board. And this setup perfectly illustrates what arc-proof compliance actually means when a fault detonates mid-service. This is governed by the IEC 60298 standard. It's basically a strict rule of 4 survival checklist that the hardware has to pass. First off, those doors, they absolutely must stay closed under the massive pressure of the blast. Second, absolutely zero hazardous parts can eject into the room where an engineer might be standing. Third, the enclosure itself cannot get pierced. Even the little visual indicators aren't allowed to burn through. And finally, every single earthing connection has to keep working, staying perfectly intact right through the middle of the fault. But here's the catch. Human error cannot be allowed to compromise that structural integrity. So physical access control steps in to back up that IEC standard. You'll see main breaker doors carrying heavy-duty padlocks or safety key locks. But here is the critical, non-negotiable rule of marine electrical safety. The breaker can only be racked in or out when the door is securely closed and auxiliary voltage is connected. In fact, mechanical interlock bars actually slide into place to physically block you. There is absolutely no open door racking allowed, ever. Let's test this out with a real-world scenario. Let's say a technician wants to rack a breaker out with the compartment door wide open, just to save a few seconds during a really stressful turnaround or maintenance window. What's wrong with this picture? Take a second and think about the actual purpose of that interlock based on what we just covered. Well, the stark reality is that literally everything is wrong with it. You must never, ever override the door-closed racking interlock. Why? Because the moment you override that rule and crack that door open to rack the breaker, you instantly strip away all of the arc fault protection that IEC 60298 is built around. If an arc flash happens at that exact moment, those thick metal-clad firewalls we talked about, they can't protect you because you literally left the front door open. Bypassing this interlock is the single most common way engineers get seriously hurt on switchgear. It completely defeats the entire safety architecture. Okay, let's move into our next section. Instrument transformers. We're going to look at sensing massive currents safely and how this whole system actually functions inside a sealed box. So here's a good question. How do we monitor these dangerous currents and feed data to our protection relays if we can't ever get near the live components, since the steel doors have to stay permanently sealed? Well, there's a fascinating divide in the technology here. Traditionally, the industry has relied on conventional current transformers, or CTs. These use a wound core or a multi-core bushing bar, but they have a major physical vulnerability. Because they rely on a ferromagnetic core, they can actually saturate during massive fault spikes. That essentially temporarily blinds your protection system right when you need it the most. Now compare that to the modern solution, the Rogowski coil. This is a real game changer. It's a flexible, non-magnetic winding. And because it totally lacks an iron core, it has zero saturation and zero hysteresis. That means its output stays perfectly linear across the full current range, no matter how wild or chaotic the fault spike gets. And this formula brilliantly illustrates the physics behind why it works so well. It shows that the secondary output voltage, U out, equals a mutual inductance constant, M, multiplied by di/dt. Now, in plain engineering terms, that just means the voltage output is directly proportional to the rate of change of the primary current, not the raw current itself. This specific trick of physics is exactly what prevents the coil from ever saturating. It really doesn't matter if the current spikes instantly. The output simply scales with the rate of that change, keeping your data incredibly accurate. 3,200 amps. When I was first looking into this, that number really stood out to me because it represents the sheer, staggering scale of measurement we're talking about here. A single Rogowski coil sensor can cleanly and linearly cover an upper range from 0 all the way up to 3,200 amps. If a short circuit instantly spikes your current from a normal 200 amps up to thousands of amps, your conventional iron core CT might just choke. But the Rogowski coil? No way. It will track that spike perfectly.
Let's bring that physics back down to earth for a second and see how it translates to the actual switchboard relays. The system takes that terrifying 3,200 amp fault current and perfectly steps it down into a tiny, completely harmless millivolt signal. Depending on your ship's specific supply frequency, it outputs just 150 millivolts at 50 Hz or 180 millivolts at 60 Hz. The winding can even stay open when the switchboard is in service. It seamlessly feeds these perfectly linear low-voltage signals straight to your protection systems, keeping the delicate relays far, far away from the lethal primary voltage.
You came into this explainer knowing that switchgear is dangerous, that now you understand exactly how those metal-clad firewalls provide real arc-proof survivability. You know exactly why the door-closed racking rule is literally a matter of life and death, and you can identify why a Rogowski coil's linear output is absolutely vital for your protection relays. The sensors tell the system exactly what's happening without saturating. But as we wrap up, I want to leave you with a provocative thought. Now that your system can sense a massive 3,200 amp fault safely, how does the system actually kill it? And how do we tackle voltage sensing using resistive dividers that never saturate? We're going to uncover the extreme mechanics of arc extinction and advanced sensing in our next explainer. I'll see you there.